Stages of memory processing. The definition of memory includes a time-dependent component in that it involves mental processes of acquiring and retaining information for later retrieval. In truth, no cognitive process is a static event, as each involves neural processing that occurs over time, even if this is only a few milliseconds. In the case of memory, the time lag between an experience and subsequent behavioral change, the operational definition of memory, can vary from a few seconds to several decades, depending on the species. For this reason, it is useful to think of memory as sequential stages of processing in which a memory is formed, stored, and then retrieved. Encoding. This first stage of memory processing is encoding, defined as the conversion of incoming information into neural signals that will be used for later processing. As outlined in Chapter 2, incoming information arrives through the sensory system, but memory encoding is more than just sensory detection. In other words, not all sensations are encoded in memory. This fact should be obvious. Few people recall every detail of a past experience, even if their memory for the event is vivid. So, what determines which stimuli and events will be encoded? Attention is probably the biggest factor, as this is the mental process that selects information for further processing. Organisms that are not attending to specific details may not remember them at all. Similarly, encoding is weaker if attention is divided due to distracting stimuli or events. Many people forget where they put their glasses, keys, or notebook because they set these down absent-mindedly while they were doing something else. Conversely, salient or very surprising events that grab attention are more likely to be encoded and transferred to the next stage of memory processing. Encoding is also enhanced by elaboration, the process of adding meaning, images, or other complex information to sensory input. A well-known elaborative technique is to tag a visual image to a person's name, e.g. the name Mark may evoke an image of a large X on the individual's chest. In any elaboration technique, the greater the level of processing, the stronger and more durable the memory. This principle is apparent in human studies. When subjects are asked to identify whether letters were written in lower or uppercase, they do not remember a word list as well as when they are asked to make a judgment about the meaning of a word. It is difficult to instruct animals to elaborate on information during memory encoding, so it is not clear whether this process is unique to humans. This seems unlikely, however, given that one of the most effective elaboration techniques is to process information in terms of its survival value. Indeed, humans have a better memory for words that they are asked to think of in terms of survival in an ancestral environment compared to modern-day scenarios. See Figure 3.2. A critical feature of the study is that the words to be remembered were the same. The difference was the instructions of what to think about when they were being read. Because the later memory test was a surprise, it is unlikely that subjects were trying to memorize the words during reading. Figure 3.2. Memory for stimuli associated with survival in the natural environment. Participants were asked to read a list of words and imagine how relevant each of the items would be for surviving when they were stranded in the grasslands or a large city of a foreign land with no resources. They were also asked to rate other aspects of each word, including pleasantness. Importantly, the words to remember were the same in each condition, only the imagined scenario was different, ancestral or modern. In a later test, recall was greater for words in the ancestral condition, but there was no difference in pleasantness between ancestral and modern conditions. Okay, so you have two side-by-side bar graphs, and the two categories on the x-axis are ancestral and pleasantness, and in the second graph, modern and pleasantness, and on the y-axis is the proportion of correct recall from 0.2 to 0.6. Okay, so when comparing ancestral and pleasantness, wow, they recall twice as much ancestral words as pleasant words. And then when you compare modern to pleasantness, it's quite similar. They recall a similar number of words. One of the challenges to encoding and to memory in general is that there is a limit on the amount of information that the nervous system can process. A partial solution to this problem is to reorganize discrete elements of sensory input into larger units. Miller in 1956 coined the term chunking to describe this process, suggesting that it increases memory capacity by reducing the amount of information that is encoded. For example, most people would have difficulty remembering this list of 39 letters. And it just says in one string, letters grouped together form chunks of words, but could easily recall the string of words that they form. Although chunking reduces the number of items to be encoded, it increases the amount of information that is conveyed in each unit. This conversion from small to larger units requires cognitive processing. The associated mental effort decreases as experience with the chunking increases, e.g., reading becomes easier with practice. Beyond the obvious example of reading, combining information into meaningful units facilitates encoding in a variety of tasks. Performance in memory tasks is increased in pigeons, rats, and monkeys when the animals can chunk stimuli or responses into meaningful units. Indeed, chunking is used to explain a number of cognitive abilities in animals, including serial list learning, covered in Chapter 6, timing and counting, and knowledge of kin relationships, covered in Chapter 10, social competence. The important point to remember is that the conversion of smaller elements into larger groups of elements provides evidence that encoding is not a passive transfer of information. Rather, it is an active mechanism that can be facilitated by cognitive processes such as attention, elaboration, and chunking. It should go without saying that better encoding leads to better memory. Consolidation. The second stage of memory processing, consolidation, is defined as the process of modifying encoded representations so that they become more stable over time. The time-dependent property of memory consolidation was recognized by the early Greeks and confirmed by clinical reports in the 18th century, in the 1700s. The latter described head trauma, producing amnesia for events in the recent, but not the distant, past. This phenomenon has been reproduced repeatedly in the lab with electroconvulsive shock, drugs, distracting stimuli, and new learning, all of which disrupt the transfer of recently acquired information into stable memories. Conversely, drugs that increase neural activity associated with learning will improve memory if they are administered immediately following training. If the time between learning and drug administration is delayed, from a few minutes to a few hours, the facilitating effect is lost. The interpretation of these data is that consolidation takes time. Memories are not stable until this process is complete. Box 3.1, Flashbulb Memories. What were you doing when you learned that? Depending on an individual's age and where they live, the completion of this sentence could read, John F. Kennedy had been shot, John Lennon was dead, Margaret Thatcher had resigned, or planes had crashed into the Twin Towers in New York City. The commonality in all of these examples is that they elicited strong emotional reactions. Most people claim to have vivid memories for at least one of these events, or more precisely, for the circumstances surrounding the news about the event. Brown and Kulik, 1977, coined the term flashbulb memories to describe these very detailed and vivid snapshots of the moment when an individual receives emotionally arousing news. They speculated that flashbulb memories differed from other, less reliable memories, and that they created a permanent record of the details and circumstances surrounding the event. Animals cannot tell us what they were doing when, but hundreds of experiments using a variety of different species confirm that emotionally arousing events are more likely to be remembered in the future. The effect depends on the release of stress hormones, which travel through the bloodstream and into the brain, causing neurochemical changes in the amygdala, a small almond-shaped structure located in the temporal lobes. Neuroimaging studies in humans confirmed that increased activity in the amygdala during consolidation improves accuracy in a later memory test. Importantly, the more shocking or emotionally arousing the event, the more likely it is to be remembered. Flashbulb memories are discussed most frequently in terms of unpleasant events, but highly emotional events that are pleasurable may also enhance memory. The evolutionary explanation for flashbulb memories is straightforward. Emotionally arousing stimuli are likely to signal important events, so it is adaptive to remember the conditions under which these occurred. Despite personal reports, not all research supports the phenomenon of flashbulb memories. The main point of contention is whether events surrounding highly emotional occurrences are remembered more accurately than other memories. In these studies, subjects are asked to remember what they were doing when they heard the news about an emotional event, not details of the event itself. One thing is true across all of these studies: people are more confident that these memories are accurate, regardless of whether they actually remember more details. This is perhaps what makes flashbulb memories unique, the certitude with which people recall these events. But why emotions would enhance confidence in memory without necessarily improving the memory itself is still a mystery. Some researchers distinguish between consolidation and a later storage phase, listing 4 rather than 3 stages of memory processing, i.e., encoding, consolidation, storage, and retrieval. The problem with postulating a separate storage phase is that it infers that representations of memory sit undisturbed in the brain for an indefinite period of time. This seems unlikely given the ongoing neural processing that characterizes cognition. It is more parsimonious, therefore, to think of consolidation as a process with 2 stages. The first occurs within minutes to hours and is dependent on protein synthesis. This early stage consolidation has been observed in a variety of species including worms, flies, and mice. In all of these studies, disruption of protein synthesis in the period immediately following learning disrupts memory formation in the same way that concussions produce amnesia for events preceding the trauma. The second stage of consolidation, which may take weeks to years, has only been characterized in mammals. This process involves structural changes in synaptic connections between neurons and a shift in the brain areas that store memory-related information. It is very likely that this second consolidation phase is present in other animal classes, i.e., non-mammals, but the details have yet to be worked out. Regardless of whether consolidation is a 1 or 2 stage process, it appears that all memories are labile before they become consolidated. If this is true, what is the evolutionary advantage of a memory process that takes time to stabilize? One answer is that the nervous system would quickly become overloaded with useless information and precious cognitive resources would be wasted if consolidation occurred instantaneously. A more direct explanation is that consolidation provides a time frame in which the representation of a memory can be modified, taking into account both confirmatory and contradictory evidence. In this way, associations between events and generalizations across conditions can be incorporated into memory for a particular event. Put simply, a snapshot of the environment provides less meaningful information than does a moving window of time. Conversely, it is possible that consolidation is not adaptive, but an artifact of brain biology. Both protein synthesis and the structural rewiring of neural circuits take time. Perhaps consolidation takes time simply because it relies on these pre-existing processes. Retrieval. Information that is encoded and consolidated must be accessed if it is to guide behavior at a later time. Retrieval, the third phase of memory processing, is the mental activity of accessing this stored information. There are 2 mechanisms by which information is retrieved: recognition and recall. Recognition is the act of identifying information as familiar, even if the details of the memory that accompany it cannot be specified. Recall is a more cognitively demanding task of generating information from memory stores in the absence of cues or reminders. Recognition retrieval is much easier than recall retrieval. It may be difficult to generate the name of a previous head of state, prime minister, or president, but most people can identify his or her name in a list. Both recognition and recall are better if they occur in the same context in which the member was encoded. Context refers to the combination of cues, both internal and external, surrounding an event. These may include sensory signals, such as specific sights or sounds, as well as hormonal or emotional states. One of the best examples, shown in Figure 3.4, is that memory is enhanced when encoding and retrieval occur during the same phase of the circadian cycle. In this study, golden hamsters did not show any evidence that they remembered an environment where they had received a shock if they were trained and tested at different times of day. This suggests that time of day information may be coded as part of the memory formation, such that circadian cues can facilitate memory retrieval. These cues may be particularly important in the natural environment because biologically relevant events often occur at the same time of day. The fact that memories can sometimes be retrieved in one context but not another supports the idea that forgetting is often a failure of retrieval, not a decay of the memory trace. Figure 3.4, Circadian-dependent memory in hamsters. A. Over a series of conditioning trials, hamsters experienced shock, random presentation of 3 to 4 mild shocks over 5 minutes in one side of a place preference apparatus. On alternate days, they were placed in the other side with no shock. Conditioning sessions always occurred at the same point in the circadian cycle. B. No shocks were turned on during a subsequent test when animals had access to all compartments. Hamsters avoided the shock-paired compartment only if testing occurred during the same phase of the circadian cycle as training sessions. Okay, so in the top diagram you can see a hamster, and then there's 2 compartments and a little tunnel between them, and on one side they're getting shocked, and on one side they're safe. Then under that you can see a side-by-side bar graph. On the x-axis is training testing time, and the sets of categories are night-night, night-day, day-day, and day-night. And on the y-axis is the time in the compartment in seconds from 0 to 600. The 2 categories of the bars are shock and safe. Okay, so you can basically see that if night and night for testing and training line up, and day line up for testing and training, the animal will avoid the compartment at that time of day. Whereas if the shock occurs at a different time of day than the training, then the animal will go to that compartment. The inability to retrieve a memory is not the only problem that arises during the third phase of memory processing. Just as consolidation does not produce a snapshot of past events, retrieval does not access a replica of the stored information. Bartlett, 1932, was one of the first to propose that memory retrieval combines elements of the encoded information with existing knowledge. His subjects recounted stories that they had read previously, frequently altering the stories to match their perceptions or beliefs of how the stories should unfold. Subsequent work verified that retrieval is a reconstruction of past events influenced by an individual's pre-existing knowledge as well as their current emotional state. Memory retrieval may also be distorted by suggestion. When false or misleading information is introduced after a memory is encoded, but then influences how the original event is remembered. See Box 3.2. Box 3.2, False Memories. Tales of dangerous or heroic deeds are often embellished in the retelling. Some of these distortions are just exaggerations or stretching the truth. In other cases, people really believe their own reconstructed descriptions of the event. But how far does this phenomenon extend? Is it possible to implant new information that is later retrieved as a memory? For over 25 years, Elizabeth Loftus and her colleagues have addressed this question with an unequivocal response: yes. Loftus's original work was straightforward. She wanted to examine the reliability of eyewitness testimony, so she showed film clips of traffic accidents to her students, and then asked them to respond to a series of questions. By altering the wording of questions, e.g., how fast were the cars going when they hit each other versus how fast were the cars going when they smashed to each other, researchers were able to modify subjects' reports of the incident. This suggestibility even extended to new events, that is, subjects remembered details that did not occur when the questions provided misinformation about the previous event. For example, subjects who read that the cars smashed into each other were more likely to report seeing glass at the accident scene. There was none. Loftus's most innovative work developed from her Lost in the Mall study. In this experiment, students were asked to reflect on specific childhood events, such as a wedding or a large celebration they had attended. One narrative, describing a day that they were lost in the mall, was fabricated. The students were told that the details of all incidents were provided by family members. 1/4 of the students reported remembering the event, and many provided specific details of what happened that day. The finding has been replicated by other researchers using a variety of fabricated scenarios, e.g., personal injury from an accident or embarrassing events like spilling punch at a wedding reception, and participants ranging in age from young children to adults. Amazingly, the more subjects think about these memories, the more detailed they become. Loftus is considered one of the most influential psychologists of the 20th century, of the 1900s, but her work is highly controversial. She argues vehemently that eyewitness testimony is unreliable, and has acted as an expert witness for a number of high-profile legal cases. Her greatest challenge arose when she questioned the notion of recovered memories of sexual abuse, pointing out that suggestibility during therapeutic sessions can create false memories for events that did not occur. Not surprisingly, these statements inflamed sentiments across the globe. Loftus maintains that her research was not undertaken as a political or social statement, but a scientific investigation of factors that influence memory retrieval. Many scientists and clinicians are reluctant to take a stand on the sensitive issue of sexual abuse claims, but few can discount the overwhelming evidence that memories may be reconstructed through suggestibility.